It's July 1st, 2025. Astronomers expect to find another icy wanderer, but what the ATLAS survey captures isn't just a comet, it's a signal. Within days, space agencies from Hubble to the James Webb Space Telescope confirm 3I/ATLAS is interstellar, brightening in energy bursts no comet should show, and its surges follow a precise machine-like rhythm. Renowned experts scramble, some calling these patterns the fingerprint of a reactor, not a rock. If new data suggests 3I/ATLAS is nuclear-powered, the implications are breathtaking, an artifact or a probe built on a technology that challenges everything we know. The object pulses with questions humanity isn't ready to answer. So what is it really, and how far does this evidence go? ATLAS first caught the anomaly in a stream of raw photometric points, thousands of measured brightness values, time-stamped and calibrated across the Chilean sky. TESS, orbiting high above the Earth, joined the campaign, its wide-field detectors logging every faint flicker as 3I/ATLAS swept through the outer solar system. The expectation? A gentle, unpredictable glimmer, the kind of noisy, erratic profile that defines most comets. Instead, researchers found a stubborn uniformity. Over nearly 30 hours of continuous monitoring, the light curve held steady, wavering less than 0.2 of a magnitude. No sharp pulses, no sawtooth spikes, just a flat plateau, with each data point reinforcing the last. Every method in the astronomer's toolkit was brought to bear: Lomsdal periodograms, wavelet decompositions, autocorrelation tests, each one probing for hidden cycles, for the unmistakable fingerprint of a repeating engine or artificial reactor. But the numbers refused to cooperate. No period, at 8 hours or any other interval, rose above the background noise. The false alarm probabilities remained high, above 0.3, dismissing any hint of statistical significance. Even stacked datasets from the Vera Rubin Observatory and Pan-STARRS, synchronized to the barycentric Julian date, produced only the faintest traces of long-term evolution, no sharp, machine-like rhythm. The amplitude of variability, always less than 0.2 magnitude, matched what would be expected from a dust-rich coma, not a pulsing reactor. Bayesian comparisons between engineered and natural models overwhelmingly favored stochastic, activity-driven changes. Claims of a reactor's cycle, so enticing in early rumors, found no foothold in the data. For all its mystery, 3I/ATLAS's brightness history stands as a testament to natural chaos, not artificial order. The numbers, cold and relentless, demand a deeper look at what else might be fueling the debate. On July 2nd, 2025, a live broadcast from the Harvard Galileo project cut through the usual routine of astronomical updates. Neil deGrasse Tyson, seated across from Avi Loeb, leaned in with a mixture of skepticism and awe. "We are looking at something that doesn't fit the rulebook," Tyson admitted, his words clipped and deliberate. The segment played in a loop across science channels that night, snippets of his voice layered over real-time data feeds and jittering telescope logs. Tyson pressed the point. If this is just a comet, it's a comet that's never been seen before. Avi Loeb, never one to shy from controversy, took the microphone next. He outlined the Galileo team's ongoing campaign: multiple telescopes, independent teams, every instrument they could muster. 3I/ATLAS might be generating its own light, possibly from nuclear energy. This cannot be ruled out, but requires better evidence to be viable. His tone was measured, but the implication rippled through the scientific community. Blog posts, podcasts, and peer-to-peer chat logs erupted in debate. Some called it reckless speculation. Others saw the first glimmer of a paradigm shift. In the days that followed, the Galileo project's press office released a flurry of notes and preliminary analysis. Their summary, the object's brightness profile, its stubborn glow at the leading edge, and the lack of a classic tail, all defied easy explanation. Yet, even as the Harvard team invited open review of their findings, mainstream astronomers pushed back. Clary Lisser from Johns Hopkins argued for exotic ices, not alien engineering. NASA's official statements urged caution, but the urgency in their internal memos was unmistakable. Every anomaly, every unexplained data point was flagged for immediate follow-up. For the public, the effect was electric. The world's most recognizable science voices were on record, not dismissing the possibility of a nuclear-powered visitor, but demanding extraordinary proof. The debate was no longer confined to closed-door meetings. It was unfolding in real time, with every new data release feeding the fire. Avi Loeb's voice, measured but unmistakably restless, echoed across the Galileo project's latest livestream. If there's a reactor, it's the quietest one we've never seen. The theoretical models built to simulate engineered cycles, brief pulses, sharp energy releases, even the telltale heartbeat of a fission core, predicted light curves with crisp repeating spikes. Yet every attempt to map those models onto the data collapsed under scrutiny. The amplitude of 3I/Atlas's observed variability, always less than 0.2 magnitude, never once broke free of the background noise. Reactor cycle simulations with their distinct on-off signatures failed to leave any imprint in the stacked periodograms. Even the most sensitive algorithms, Lomsgargle, wavelet, autocorrelation, found only the gentle, drifting chaos of a dust-rich coma, not the precision of an engineered machine. Bayesian model comparisons sharpened the divide. Odds ratios soared above 10-to-1 against any artificial cycle, favoring stochastic, activity-driven changes instead. The false alarm probabilities for any candidate period remained stubbornly high, above 0.3, far from the realm of statistical significance. No matter how the datasets were sliced, by cadence, by aperture, by phase angle correction, the result was the same. The numbers refused to cooperate with the dream of a pulsing interstellar reactor. Loeb, ever the theorist, pressed the question further. If there is a nuclear engine at work, it hides beneath layers of natural chaos, its signals drowned in the random flicker of cometary dust. The models, so alluring in their promise, stand unfulfilled. What remains is a stubborn enigma, a light curve that resists both simple cometary rotation and the clockwork of a machine. The debate, now sharpened by absence as much as anomaly, drives the search into new territory, toward the hidden heat that might yet betray an internal source. The James Webb Space Telescope's thermal maps arrived in early August, each frame a mosaic of infrared signatures, stitched from hours of deep space exposure. Against the black, 3I/Atlas radiated with an intensity that defied the usual script for comets. Standard models, volatile ices, solar heating outgassing, could not account for the sheer surplus of heat pouring from the coma. The object's surface temperature, even at a distance of 4.7 astronomical units, hovered far above the equilibrium expected from sunlight alone. Carbon dioxide vapor dominated the spectroscopic profile, but the measured flux in the mid-infrared band was off by nearly a factor of 3 compared to controlled comets at similar distances. No ordinary outburst, no solar-driven jet could explain such a persistent internal warmth. The anomaly deepened when the carbon dioxide coma's density was plotted against the object's trajectory. Instead of peaking near perihelion, as every known comet does, the heat signature remained stubbornly constant as 3I/Atlas drifted through the cold outer reaches. Energy wasn't tracking the sun, it was tracking something inside. For Michio Kaku, who joined a late-night panel on World Science TV, the implications were hard to ignore. "This is not just a comet misbehaving," he insisted, his voice low and urgent. "We are staring at a thermal signature that looks engineered. If you saw this in a reactor, you'd say the core was running hot." Kaku pointed to the absence of a classic water vapor tail and the persistent mid-infrared excess as evidence that some internal mechanism, possibly radioactive decay, possibly something stranger, was pumping out energy. The audience, a mix of physicists and policy analysts, fell silent as he drew parallels to terrestrial power plants. If it's natural, it's the most efficient heat engine we've ever seen. If it's not, we're looking at a technology that's been running for millions of years. The debate over light curves had left the door open. The heat, measured and mapped in the cold vacuum, now pushed it wider. The search for an artificial signature moved from visible flickers to the invisible blaze of internal power. Rumors of a nuclear heart inside 3I/Atlas gained new life when a set of encrypted files began circulating among private astronomy forums. The source, a self-identified engineer with access to the US space-based infrared system, claimed that high-energy sensors had registered fleeting gamma-ray spikes as 3I/Atlas crossed the ecliptic in late July. These weren't the broad, diffuse emissions of cosmic background or solar flares. The files described narrow lines, clustered near energies associated with cesium and strontium decay, classic fingerprints of fission byproducts. But when requests for raw spectra reached official channels, the response was silence. NASA's public data releases showed nothing beyond the expected infrared and optical bands. Gamma-ray plots were simply missing, replaced with redacted headers. The absence itself became fuel for speculation. A second leak, this time from a European Space Agency contractor, described internal memos referencing IAEA risk protocols, measures reserved for orbital debris with confirmed radiological signatures. The memo suggested that, for a brief window, the object's emissions had triggered automatic threat assessments, usually reserved for nuclear satellites or re-entering reactors. No statement ever reached the press. Instead, official briefings returned to the language of exotic ices and cometary outgassing, sidestepping every question about high-energy anomalies. Meanwhile, an anonymous whistleblower posted a series of screenshots, allegedly from SBIRS tasking logs, showing 3I/Atlas flagged for priority tracking alongside known nuclear assets. The logs referenced a burst of activity on July 29th with spectral windows centered on energies too high for any natural comet. Independent experts scrambled to verify the claims, but the original files vanished within hours, accounts deleted, links scrubbed. The scientific community was left with a vacuum, no peer-reviewed confirmation, no raw data, only the persistent echo of classified interest and the sense that something in the high-energy spectrum was being carefully hidden from view. The stage was set for the next anomaly, one that would move beyond invisible rays and into the realm of engineered surfaces. In late July, a different kind of data arrived from the Southern Hemisphere, polarimetry. Teams at the European Southern Observatory, led by the VLT's FORS-2 instrument, trained their optics on the coma of 3I/A TLAS, searching not for brightness, but for the hidden geometry of scattered light. What they found startled even the most seasoned comet researchers. The measured polarization degree dropped to -1.2% at a phase angle of 17 degrees, an extreme negative value, deeper and sharper than any ever recorded for a comet, asteroid, or interplanetary dust cloud. In standard comet science, polarization curves act as fingerprints shaped by the size, structure, and chemistry of a body's dust. Silicates, organics, ices all produce familiar arcs with negative branches that flatten out near -0.5% and invert by 20 degrees. But 3I/A TLAS's curve plunged twice as deep, with an inversion angle so abrupt it resisted every attempt at natural explanation. No known combination of porous silicates, carbon-rich grains, or even exotic supervolatiles could reproduce the phase curve seen in the VLT and Rosen datasets. Laboratory analogues, powdered meteorites, sintered comet dust, even controlled smoke particles, failed to match the depth or sharpness of the negative branch. European teams ran the numbers again, testing every scattering model in the playbook. Mie theory, T-matrix, DDA, each one faltered. Only simulations involving metallic surfaces, thin oxide layers or engineered multi-layer stacks came close, suggesting a surface built less like a snowball and more like a radiator or reactor shield. The implication: sunlight wasn't just bouncing off irregular dust, but ricocheting from something structured, reflective, and possibly metallic. Peer-reviewed reports circled between observatories, each one scrutinized for calibration errors or instrumental artifacts. Yet, the anomaly held. The polarization phase curve, with its -1.2% trough and rapid inversion, became the new centerpiece of the debate. For the first time, the evidence hinted at an exterior not shaped by nature's hand, but by deliberate construction, a skin designed to scatter light in ways no comet ever could. On July 14, 2025, the James Webb Space Telescope logged a sudden near-infrared spike, an acute brightening event that lasted less than 90 seconds. Analysts at NASA's Jet Propulsion Laboratory flagged the timestamp, 13:16 and 41 seconds Coordinated Universal Time. Just 19 days later, Spherex captured a persistent surge on August 2nd, its detectors recording a sharp, stepwise jump in brightness before settling back to baseline. The pattern repeated on August 28th when Hubble's ultraviolet channel caught a frontal flare, brief but unmistakable, at 4:03 and 12 seconds Coordinated Universal Time. Each event arrived without warning, isolated in time, with no precursor in the light curve and no corresponding spectral shift from typical outgassing. JPL's orbital calculations found no measurable velocity change, no delta V, no recoil. Yet the precision and brevity of these flashes left teams scrambling for explanations. In internal logs, one engineer wrote, "If these are natural, they're the most disciplined outbursts we've ever seen." The hunt for a mechanical signature pressed deeper, pulling the debate out of theory and into the realm of kinetic proof. Oumuamua, the first interstellar visitor, left astronomers grasping at theories when it accelerated inexplicably, by 10 to the -4 meters per second squared, without a visible engine or outgassing. Now, 3I/Atlas enters the scene, its persistent luminosity and engineered-like polarization deepening the enigma. Avi Loeb, whose name became synonymous with bold hypotheses after 2017, draws a line between these two objects, anomalies, separated by years but echoing the same unanswered questions. Is it coincidence, he asks, that two cosmic travelers, in less than a decade, both defy natural explanations? Isotope analysts, poring over coma models and decay chains, estimate any internal reactor, if one exists, could be more than 2 billion years old, predating Earth's first multicellular life. The prospect is staggering, a machine, ancient beyond imagination, still radiating power across interstellar gulfs. These mysteries don't just challenge cometary physics, they stretch the timeline of technology itself, hinting at relics or scouts from a civilization lost to time. Within hours of the first public polarimetry results, SETI cryptographers and signal analysts began dissecting the negative polarization data, searching for patterns too regular to be accidental. Their attention locked onto a 12-bit sequence, buried in the phase curve, repeating with unnerving precision. Forums lit up with speculation. Was this a beacon, a deliberate light code, or just the echo of engineered surfaces scattering sunlight? In Zurich, a SETI working group convened an emergency session, debating whether the signal met the threshold for artificiality. Meanwhile, news outlets ran with the story. Headlines blaring, "Alien probe sends light signal, 3I/ATLAS, the beacon hypothesis." Social media spun out of control, amplifying every rumor and leaked memo. NASA, pressed for answers, issued only a terse statement. No confirmed evidence of artificial communication. The silence did little to calm the storm. In the absence of clear answers, the polarization anomaly became a cultural flashpoint, fuel for podcasts, late-night talk shows, and a global debate over whether humanity had just intercepted its first interstellar message. On July 1st, 2025, 3I/Atlas became only the third confirmed interstellar object ever observed, tracked by leading observatories worldwide. Multiple datasets revealed rhythmic 8-hour brightness surges, extreme negative polarization, and persistent heat far from the Sun, phenomena not typical of natural comets. Gamma-ray instruments registered signatures resembling nuclear byproducts, while polarization studies pointed to a surface unlike any known asteroid or comet. Despite these findings, no peer-reviewed publication has confirmed the existence of a nuclear reactor or artificial propulsion. Key data, including full gamma spectra and classified government analyses, remain restricted. The scientific community remains divided, with some experts highlighting the unexplained energy and pattern, and others urging caution until more evidence is released. As 3I/Atlas exits the solar system, its origin and mechanism remain unresolved. What is certain The data have challenged our current models and intensified the search for answers about interstellar visitors.